Let's move on to the E in the ADMEs, excretion. And excretion really means the removal of a drug or its metabolites from the body. And a more general term is elimination, which is broader and includes the metabolism. So it encompasses metabolism and excretion. The first thing what we need to discuss are kinetics of elimination. Because there are two different forms that we should be familiar with, one being responsible for the majority of the drugs, and this is called first order kinetics. And if you are looking at such a plasma concentration over time, what most drugs do is that the more drug you're going to have, the more is going to be eliminated. And then it's kind of leveling out in the end. What that translates to is that the amount of drug decreases by the same, and now important, percentage or fraction each time period. So the more you throw in, the more is going to be eliminated. And why is it happening? Because we usually have plenty of enzymes that are going to work on, and so the more you use drug, the more enzymes are going to work on it, the more is metabolized, and the more is going to be excreted. And so the elimination is a constant percentage over time, which means it's dependent of the plasma concentration. And so most drugs are eliminated first order kinetics. There's another type of kinetics, and that's called zero order. And if you plot this, you're not going to have this exponential curve. You're just going to have a line, a linear relationship when you plot the plasma concentration over time, and that's called zero order kinetics. And that's what hardly any drugs fall into this category. The most famous example is probably alcohol. And then there's also other drugs that you're going to learn about, like phenytoin, an anti-seizure medication that is pretty famous for being eliminated zero-order kinetics. But 99% of the drugs fall into the category of first-order kinetics, where there's the same percentage each time period eliminated. And here, for the zero-order, we can use the same words and just replace the percentage, so the amount of drug decreases by the same, and now we're going to put in amount. So it's always the same amount each time period. So that's not dependent of CP. And it can also happen to remember, well, if you drink a lot of alcohol, it's not like you're going to metabolize more. You're always going to metabolize the same amount each time period. Let's say 1 drink per 2 hours or something like that. That also explains why alcohol builds up so quickly in our body. Now I want to spend some more time on the first order kinetics. So this is an exponential curve, and what we can do is to get a line, we're going to plot it on a logarithmic paper. So we're going to put the plasma concentration on a logarithmic paper, and if you plot it over the time, we are going to get a straight line. And that's mathematically always more easier to handle. We can do more with it. For example, if you want to determine the volume of distribution, what we discussed in another video, we can extrapolate the line to the time point 0 and get our CP0, for example. Another thing what we can get from such a line, we can easily read off, let's say, the half-life. How is a half-life defined? I hope you're going to say it's the time it takes to eliminate 50% of the drug. And why is it easy to read off such a line? Well, let's suppose I have here 4 milligram per liters and here 2. And so I know, okay, that's where it's going to go into halves. And I have here some hours, 1, 2, 3, 4. So then I can say, okay, from 4 to 2, once it divides into half, okay, these are gonna be 2 hours. So my half-life is 2 hours, for example. So very easy to read off such a line. Now another parameter that we should know about is something called Ke, which is the rate constant. The rate constant correlates with the slope of the curve. And because it correlates with the slope of the curve, we can say Ke equals delta log Cp divided by delta T. So we can now use any slope, any points that we want to use. So we could say we go here from, let's say this is 1. We go take some sort of this is rise, and that's a run. So let's suppose this is 8 hours. And let's say this is log 4 minus log 1, if we use this distance here. And this is then 8 minus 2. And I didn't put the whole formula in because we have to also put in the log. We have to use this number minus 2.3 to calculate the log in. But then we can use any numbers for this delta, so the difference between two concentrations and 2 times. And then I'm going to get, when I put in some numbers, I'm going to get my Ke, so my rate constant. Why is that also an important thing? Well, I can also get my half-life from this rate constant, because there's another important formula for half-life. So, I mean, I can either read it off the graph, as I showed you before, or I say T half equal 0.69 divided by Ke. Now the 0.69 come from the natural log of 0.5, because obviously if you want to do the half-life, you need to use the numbers where the drug concentration goes into half. And again, we always have to have this additional multiplicators because we need to calculate the log from the natural log. So in case I'm given the Ke, I can from this also calculate the half-life with this 0.69 in the denominator. So when we're talking about elimination, here are a couple of formulas that you should be aware of. How to get Ke, how to get T half-life from Ke, as we just explained. Just wrote this down again. Another important key parameter for elimination, where Ke also is going to come up, is clearance. And the clearance is a measure of the removal of the drug from a body. And the clearance is defined by Ke, which tells us something about how fast is the drug eliminated. But also we need to put in here the volume of distribution. Where does it come from? Where do we find it? And that defines clearance. So clearance is the volume of plasma that is cleared of drug per unit time. So clearance is a flow. The units are milliliter per hour or per minute. Clearance is related to both the volume of distribution, and Ke. And it's another very important parameter that we need to consider when we're dosing drugs, when we want to know something about their process of elimination.